Okay. So I will discuss. So yesterday we arrived. We conjugated the linearized operator at the Stokes wave to an operator which is J and B. B is self-adjoint, and it has the structure. So the operator L is complex Hamiltonian, and the operator L is also complex reversible, in the sense that it's Q commute with this reversibility. And moreover, we know everything about the spectrum of this operator. So, and then recall that what we want to do, if we know that we want to understand the spectrum of the operator on L2 of the torus of L mu epsilon. So this is the question. And what we know is the spectrum on L2 of the torus of the operator 0, 0. And what we know is that it has 0 as an isolated eigenvalue with as 0 is an isolated eigenvalue multiplied with 4. All the other spectrum of this operator stays on the imaginary axis, and it is isolated. It is separated by the 0 eigenvectors. And moreover, what we know is that we also know the eigenvectors of 0. Actually, we know the generalized eigenspace of 0. So we know that the generalized kernel is spanned by the 4-vector F1 plus, which is given by cosinus of x sinus of x, F1 minus, which is given by minus sinus of x cosinus of x. Then we have F0 plus, which is 1, 0, and we have F0 minus, which is 0, 1. And we know that these three are eigenvectors. These three, these and these are eigenvectors, and this instead is the generalized kernel. Okay, so we have the basis of the generalized kernel at 0. And what we want to understand is at 0, 0, the spectrum at 0, 0. Okay, and what we want to understand is so long as we switch on mu and epsilon, and we want to see what happens to this eigenvector. When epsilon becomes larger than 0, we want to see if they split and how they split. Okay, so how do you control this? So so this is a problem. So this is a bifurcation problem from a multiple eigenvalue. So if you have a single eigenvalue and you want to continue it, you can continue the eigenvectors, the single eigenvectors. But if you have a multiple eigenvalue, it is much more difficult to continue the single eigenvectors. It actually you should not. You should not try to prolong the eigenvectors. The correct object that you need to prolong the spectral projector. Because this is the object which is analytic, the parameters. But the eigenvectors will not depend regularly in general on the parameters. It's much more difficult to prolong the eigenvectors. So what I will prolong, I will transform these in the basis which depend analytically on the parameters. If they
assuming that you select, there is a problem of selection.
If there is a problem of selection, but the spectral projectors does it automatically. The spectral projectors is the object which is analytic in the parameters.
Yes, but if it's split, when you select this one is the first one, this one is the second one.
But you don't know how they split. And if this is also a point. So there are points along the. So there are you can select the parameters so they don't such code they may not split completely. Okay, so and the theory which tells what goes like this actually is very well known, and is in the first 30 pages of Catu's book. This is something very classical, but I want to failed to you because it turns out that it's very powerful. So the lemma is this. So we start with a very general lemma, which is this. I take P and Q, which are projectors, and such that the norm of the projectors is smaller than 1. Then there exists an operator U, a variable operator U, such that U conjugates the two projectors. So such that U is equal to U P U minus 1. And in particular, U goes from the range of P into the range of Q, and it is an isomorphism. And so in particular also the dimension of the range of P is also equal to the dimension of the range of U. Okay, proof? Okay, proof. So you see that now I will construct U, then we construct it. I will give a formula for it. So what is R? So let me define R, which is P minus Q squared. So this is P. So I have P squared, which is P because there's projectors. Then I have minus QP minus PQ plus Q squared, but use a projector, so it's Q. And then let me compute the commutator between R and P. So the commutator between R and P is what? So I have P. So this is RP minus P R, and what it is? So I have P is P squared, which is P, minus Q P squared is P, minus P Q P plus Q P, and then I have minus P applied to R, so minus P plus P Q P plus P squared is P PQ minus PQ. And so if I didn't make mistakes, so this cancel, minus QP plus QP, my plus PQ minus PQ minus PQP plus PQP. This is so I commute with P, and the same computation tells you a similar. Now the computation tells you that P commutes also with Q. And now put U tilde, which is QP plus identity minus Q, identity minus P, and put V tilde, which is PQ plus identity minus P, identity minus Q. And you see that U tilde, this goes from the range of P into the range of Q, and this instead goes from the range of Q into the range of P. And moreover, also this also sends also the range of 1 minus P into the range of 1 of identity minus Q, and also this send the range of identity minus Q into the range of identity minus P. And then if you compute U tilde composed with P tilde, what do you get? So let's try to do this. So U tilde composed with P tilde, so I have first QP composed with PQ, so I get 2PQ. And then I have this composed with the first part, but here I have identity minus PP, so this becomes 0. And so then I have this composed with the first one is 0. And then I have identity minus Q, identity minus P, identity minus Q. And then you do again a bit of computation and you find we can do them or not, but it's right. And if you compute this, you find that this is exactly identity minus P plus PQ plus QP minus P. And this object is already written on the blackboard, and it is minus R. So it is identity minus R. And if you do the computation and you find that this is also equal, you get the same result if you put the tilde. Okay? And now we are done because what happens if you define U as identity minus R to the minus 1 U tilde. And this object is defined by normal series because the norm of R is smaller than 1. So the identity minus R to the minus 1 you can define by normal series as the sum of minus 1/2 over n of minus R to the n, and this is well defined because the norm of R is strictly smaller than 1, and it is strictly smaller than 1 because of the assumption that the norm minus U is smaller than 1. And similarly, you define V as identity minus R to the minus 1/2 tilde. Okay? And now what happens if you do UV? So if you do UV, you get what? You get so you have identity minus R minus 1/2. U tilde is written there. It is QP plus identity. So let me keep it like this. Sorry, U tilde, and then V is this. Okay, but remember that R commutes with P and Q, and so R commutes first with P tilde because with tilde is just made of P and Q. So you switch them. So you have here the tilde, identity minus R to the minus 1/2, but this is identity minus R. And so this is the identity. And moreover, second point is this. So this is the first point. So the second point is if you do U tilde P, what do you get? U tilde applied to P. U tilde applied to P survive only this term. So this is to P, but this is also equal to U tilde if you apply on the left Q. Okay, because Q U tilde is square is a projection to P, and this instead is 0. And then you have also the similar computation that P d tilde is equal this time to PQ, and is equal to d tilde Q. And so what do we conclude? So we conclude that what do we get? We get that if we make U apply to P, what is this? U apply to P is identity minus 1/2 U tilde applied to P, but U tilde applied to P is what? It is Q U tilde. So this is identity minus R minus 1/2 Q U tilde. Q and this object commutes. And so the very end, what is this? This is Q applied to 1 minus R minus 1/2, which is U. This is QU. And so you see that U conjugates the two projectors. And so this proves the lemma. So in particular, there's range of projectors are isomorphic and the dimension is the same. The dimension of the image is the same. All right, so application. So let me define the spectral projector applied to the spectral projector on the spectrum of the operator. So let me take a circuit. So I take the spectrum. So the L00 as an isolated eigenvalue. So I take a circuit. I take a circle which isolates 0 from all the other eigenvalues. Is sufficiently large. So let's say these are at distance 1. So we say that this can be a distance 1/2 from 0. And I take it, so this is gamma, I take it counterclockwise oriented. And then I define the spectral projectors, which is P mu epsilon, which is minus 1/2pi, the integral over the circle gamma of L u epsilon minus lambda to the minus 1 in the lambda. And I claim that one P mu epsilon is well defined. P mu epsilon is a spectral projector, is a projector which commutes with L. And this is also spectral projectors, which is norm close to P00, provided mu and epsilon are sufficiently small. Okay, so what do I need to do? Okay, so let me sketch the so so what do we need to do to prove that is well defined? Well, I need to prove that so this is a circuit which isolates the spectrum of L00 from the spectrum of the rest, but instead here I'm integrating the resolvent of L mu epsilon. So I need to prove that gamma is still in the resolvent of L mu epsilon, if provided L mu epsilon are sufficiently smaller. Okay, and this is a perturbation argument. So here you can work L mu epsilon minus lambda. You work perturbatively. So this is L00 plus minus lambda plus R, let me call R mu epsilon. R mu epsilon is the difference between L mu epsilon minus L00. And you can also check that this operator R mu epsilon is an operator reducible from this operator from H1 to L2. The difference is negative. But if lambda is in gamma, then this object, the unperturbed solvent, it is also well defined. And if this is object, you can check that it maps L2 into H1. And you can also check that the norm L001 minus lambda applied to R mu epsilon as an operator from L2 to L2 is so it is bounded and the norm is smaller than 1 because R mu epsilon is the difference between L0 and L0. And so the object is as sides as the both sides, either in mu or epsilon. And so this is smaller than 1, provided the mu and epsilon are sufficiently smaller. And so what you see. So you see that L mu epsilon minus lambda to the minus 1 can be defined by normal series as identity plus L00 minus lambda minus 1 mu epsilon to the minus 1 applied to L00 minus lambda minus 1. And so you see that you define by normal series, and so if lambda belongs to gamma, then it is also the resolvent of the vector operator, and moreover the vector operator. So this is bounded L2 L2. This instead is a derivative because it goes from L2 to H1. Okay, and so what you get is also that this operator has a compact. And so this operator has only the few points. Okay, and so here what you get is that lambda in gamma, lambda belongs to gamma, and lambda belongs to the resolvent of this operator. And
So we get you are going to always say
yes,
this will cross the gamma.
no, no, you stay inside. Gamma is lateral. Gamma is equilateral. Gamma is at distance 1. And instead take a values, we move. So gamma is at distance 1. And instead the grade is a much smaller size. So the grade will stay inside here. And instead this is a distance 1. Is a distance 1, and instead the figure 8 is it is a distance epsilon. It's the distance epsilon. So the figure 8 is the vector picture with the scale. So the figure 8. Yeah, so this distance is about epsilon. And instead the circuit you take it much larger. But the next value is a distance 1. So you have space. Okay. So do you know that these are projectors? This is clear. P square is equal to P. Wow. Yes.
Yes. I don't know. Don't ask me. You question Paolo because of the end people saprei. But at least a mind.
Paolo is brave at once. Okay, so no, then I leave. Okay, this is more or less okay. This is quite standard that you can construct the projectors integrating over the solvent of the circuit. So let me. So if there's an exercise, so who is an exercise then? Exercise in complex analysis. Okay, and instead the 3 also is more or less clear now because this is the second resolvent identity. So if P mu epsilon minus P00, this is a minus 1 over pi integral over gamma, then you have the difference of the resolvents, but the difference of the resolvents is L mu epsilon minus lambda minus 1, and then up to a sign which I never remember, probably changes, and then you have the difference L mu epsilon minus L00, so we have the R to epsilon L00 minus lambda to the minus 1 in the lambda. And so by using this formula and the bound, so this by using this bound and now this bound that you get from the solvent, you also find that the norm of P to epsilon minus B 00 is smaller than 1, provided that fewer epsilons are sufficiently small in such a way that the norm is okay. The norm of this is provided fewer epsilon. Okay, by using this and the bound okay. Okay, so now let me define V mu epsilon as the range of P mu epsilon. Then, so this is a projector, so P commutes with L mu epsilon, which is clear from the formula, from the definition. And so what we have is that for sure this is an invariant space for L mu epsilon. So L mu epsilon goes from V mu epsilon into V mu epsilon and to the spectrum of L mu epsilon inside the complex number inside gamma coincide with the spectrum of L mu epsilon restricted to the space, to the epsilon. So all the spectrum of L mu epsilon inside the circle, inside here, is actually the spectrum of L mu epsilon restricted to the space. And by what we told before, so the dimension of V mu epsilon is equal to the dimension of V00, and V00 is the range of the Ampere-Tour projectors, and this we know, and so the space is exactly the span. This is exactly spanned by these four vectors, because these are the four vectors. Yes.
Sorry, probably I missed it, but how do you know that this L2 to L2 norm is order epsilon?
This one,
Yes.
you get the smallness by atom. You get the smallness because so when so take the difference. So this at epsilon equal to epsilon equal to 0. This is exactly L00. And so when you make this, so you need to write explicitly. I can write explicitly. Let me write explicitly with this guy. So R mu epsilon is this guy. R mu epsilon is this ds plus I mu p epsilon mu. So in the computation here you get the mu sine of d plus the projector on the 0 mode, and here you get the minus a epsilon, and here you get the p epsilon ex plus mu. And if you remember from yesterday, a epsilon b epsilon outside epsilon. So this is epsilon, and it is volume. Sì, sono modulus of d plus mu minus modulus of d. Se vuoi moltiplicare sopra più espandi, you get and then you need to control the derivative. You lose one derivative, but you regain the derivative by the Ampere-Tour result. Okay, so the Ampere-Tour space V00 is spanned by F1 plus and minus and F0 plus minus. And moreover, what we can do is also, so we know a map, we have a map. So calculate as a map which transform the unperturbed space into the perturbed one. So if I define mu epsilon as the Kato transformation operator, which was reading as identity minus P mu epsilon minus P00 squared to the minus 1/2 applied to P mu epsilon P00 plus identity minus P mu epsilon identity minus P00. Okay, so this is the object which conjugates the two projectors. This is the object that P mu epsilon is equal to U mu epsilon P00 U mu epsilon minus 1, and moreover, U mu epsilon send is an isomorphism between the unperturbed space into the perturbed subspace. Okay, so these properties, so the all perhaps are okay. You want some details on this or go on? Okay. No, the only thing which perhaps is not completely clear is the property 2. I can convince you about this or leave it as an exercise and move on. What do you want, the young guys? Please, I move on. Excellent. Okay, now I insisted a lot yesterday. No, I didn't. No, it's here. I insisted a lot yesterday about the fact that L is a Newtonian and reversible. And what about the projectors P mu epsilon and U mu epsilon? So they inherited some properties, and the properties are these. So one P mu epsilon. So what should we expect? So it is so in Catholic book or in a book in which all these theories, for example, another book in which this theory is written pretty well is the Islop-Sigal quantum mechanics, they go through all the construction. And then what is standard, both in CAT or in this, in the other books, it is. So if you start with an operator which is self-adjoint, then the spectral projector is orthogonal and the transformation operator is unitary. But now we start from an operator which is not self-adjoint, it is a Hamiltonian, and you have a counterpart. And you have that P mu epsilon is skew Hamiltonian. Meaning that P mu epsilon star J is equal to J P mu epsilon. And it is also L mu epsilon is reversible and Q mu epsilon is reversibility preserving.
Alberto, a stupid question, but if you press for square Hamiltonian, you just have to write by E, the operator, you get self-adjoint, you apply the machine of self-adjoint. No? It doesn't work then?
No.
No, I know this is super stupid.
It doesn't work because it's a matrix, it's an operator. So this would work for I something. Cioè for a scalar operator. This would work. But this is a matrix operator.
No. You need in any case a unitary to bring so at this point it was more or less equivalent to what you have to
Yes, cioè if it is
If
scalar,
it's scalar, but it's not scalar, so you
It
need
is
to
not
use
scalar.
the unitary operator.
Yeah.
Which means that you have to do the machine with your
but u mu epsilon is not.
No, but my mind was doing the
Okay.
scalar. But it's
The
scalar,
scalar
it's
works.
not a scalar. So you have to use, to define a unitary operator, then. This is roughly speaking, one way to interpret what you're doing.
Yes.
So, there is no economic at the bottom.
No. No. Okay, so P mu epsilon is the versatility preserving, meaning that P mu epsilon composed with rho bar composed with P mu epsilon. U, and the second property, what about U? So U mu epsilon is symplectic. So U mu epsilon star J U mu epsilon equal to U mu epsilon, and reversibility preserving. And the third property that you can prove is that P0 epsilon and U0 epsilon are real operators, meaning that it sends real vectors into real vectors. Okay, so let me prove 1, 2, and then I leave 3 as an exercise. Let me prove 1, 2. Let me sketch a proof of 1, 2. Okay, so L mu epsilon J, what is L mu epsilon J? So this is J B mu epsilon J, and so this is J, and I can now read this as L mu epsilon star with a minus. And so what does it mean? This means that L mu epsilon minus lambda J is equal to minus J L mu epsilon star. So I subtract lambda on both sides, so here I get plus lambda. And so from this, I learned that if lambda belongs to the resolvent of L mu epsilon, then also minus lambda belongs to the resolvent of L mu epsilon star, which is not the standard. Not the standard is where is that if lambda belongs, then lambda conjugate belongs to the resolvent of this. But since this is Hamiltonian, I get something more. This is not the Hamiltonianity. Hamiltonianity has something more. So if lambda belongs to the resolvent of L mu epsilon, then minus lambda, so without the conjugate, belong to the resolvent of L mu epsilon star. It's from Hamiltonianity. Okay, so now I invert this, and so if I invert it, you get that J L mu epsilon minus lambda minus 1 is equal to minus L mu epsilon star plus lambda minus 1 J. And so now I want to take P mu epsilon. So P mu epsilon, P mu epsilon is minus 1 over 2 pi. Minus 1 over 2 pi. So that what does it mean, the integral? It means that I'm integrating by definition along, so I choose a parametrization, gamma t. I choose a parametrization gamma t along the curve gamma, which parameterize. And so this is L mu epsilon minus gamma t to the minus 1 gamma dot p dt. And then what I want to do is to compute the adjoint. So the adjoint, I need to take the adjoint of this operator. So this number, the I becomes minus I, so here I get a plus. Here I get an adjoint, and when I go inside with the adjoint, I get here lambda star, and here I get gamma conjugate, and here I get the conjugate. And then what is this circuit now? So now I'm not afraid, I'm not afraid because this is a circuit minus gamma t. So if gamma t is counterclockwise, this is rotating clockwise. And so exercise for doing complex analysis, convince yourself that this is 1 over 2 pi, the integral over gamma of lambda mu epsilon star plus lambda minus 1 in the lambda. And do it, you can do it by choosing gamma t. Just choose gamma t as, for example, t 2 pi t, 2 pi I 2 pi t, just a circle, which is fine in our case. And this allows you to do a computation quite explicitly. Okay, and now what do we get? Now P mu epsilon star applied to J to this, so I have this formula, I need to apply J. I need to apply J on the right, and J on the right. So apply J here, which means that I get this. And this tells me that I can commute these two, but I need to check the result is on the can commute. So I have an identity, no? I apply J, I use this identity. And these identities, there is a minus here, and the minus will change the sign here. And so this identity tells me that it is minus 1 over 2 pi integral over gamma of J L with epsilon minus lambda minus 1 lambda, and this is exactly J P mu epsilon. So since we are doing the Newtonianity, let's do immediately this then. So what happens now if I do J mu epsilon? So J mu epsilon is J. What is u mu epsilon? U mu epsilon, I have the formula here. So I copy it. Identity minus P mu epsilon minus P 0 0 squared minus 1 alpha P mu epsilon P 0 0 plus identity minus P mu epsilon identity minus P 0 0. And now what happens? Now I use this one. I use this identity, which tells me that every time that I commute J with the projectors, I need to switch the projectors with its adjointer. So let me do it. Let me do this. So okay, so it's pass, and every time you need to take the adjointer. So this becomes identity minus P mu epsilon minus P 0 0 squared minus 1 alpha adjointer apply to P mu epsilon adjointer P 0 0 adjointer plus identity minus P mu epsilon adjointer identity minus P 0 0 adjointer J, right? And what is this? So this is the adjoint here, I mean adjoint everything. So this is a big adjoint of, okay, the big adjoint of water. So remember that this in any case commutes with the projectors. So I can keep it also, I can always keep it here. Minus 1 alpha, and here instead I have P 0 0 P mu epsilon plus identity minus P 0 0 identity minus P mu epsilon star. And what is this guy? This guy. We have already seen this as well. We have already seen this. This was on the blackboard already. This was V, the brother of U. And V was also the inverse of U. So this is U epsilon minus 1. So all of these, what does it prove? So this proves that J U mu epsilon is equal to U mu epsilon star minus 1 J. Now apply U star with epsilon and you have them on this object.
Yeah, just like that.
Just
It's J at the right hand side.
sure.
Yeah, otherwise.
Otherwise, too many you.
Yeah, otherwise this seems like big stronger.
It's a bit straight. Okay. Okay. Okay, the simplicity and then the reversibility you prove in similar way. Okay, so let me skip this, but find the details in the paper. So the rest is let me go on. Let me go on. Let me go on. Let me go. Yeah. And the other properties you prove in a similar way. So by playing with the projectors and the definition of the object. Okay, fantastic. So consequence. So okay, so we have a basis of the unperturbed spectrum. And now we have the Kato transformation operator. Kato transformation operator allows us to transform the unperturbed basis into the perturbed basis. So now, meaning by Kato, if I define F1 plus minus mu epsilon as the transformation operator, mu epsilon applies to F, the unperturbed one, F1 plus and minus, and F0 plus minus u mu epsilon equal to u mu epsilon F0 plus minus, then so V mu epsilon is spanned by these four vectors. So this is a basis of the perturbed space. So you see, I'm not claiming, and they are not, so they are not eigenvectors. I'm not claiming that they are eigenvectors. So what I'm claiming is that they span the basis. They don't span the basis, they span the space. So they are a basis of the perturbed space. And moreover, something else. So you see the P mu epsilon, which is never, it's not anymore on the blackboard, but P mu epsilon.
No, but they are not eigenvector of those your original problem, but of the some transform of the complement, yes.
No, these are the correct eigenvectors. So these are a basis. These are a basis of the perturbed space.
Exactly. So you apply a transformation. Those are mapped on a base.
Yes, this is the base of the perturbed space. So this means that the spectrum close to zero of the operator L mu epsilon, which coincide is this. So by this, the spectrum of the operator near inside the circle gamma, near zero, is the spectrum of the operator restricted to the space. So this describes the spectrum. So this I have vectors which span the space.
Yeah, but not only those vectors determined by the simplistic transformations.
This will give an additional property of these vectors, which are now of these four vectors, which are now 10. Yes.
So simplicity is not necessary just to say base to base.
No,
But
No.
because
it will give us something.
you need some invertibility or something. So essentially, what you need, you are not saying that in principle you are not necessarily using orthogonality.
No. No.
So angles can change.
Yes. But yes. In principle, yes.
In principle, yes. But then you exploit the
I exploit.
you epsilon is split.
yes, to say that also these vectors have additional properties that now I tell in a second, but I'll tell you in a second, but first let me stress one more thing. So so the method that to mu epsilon it associate L mu epsilon is analytic because of the object depend analytically over epsilon. And so the projectors, the map that to mu epsilon, so the map mu epsilon it associate the spectral projectors. So mu epsilon enter just in the solvent. So this is also analytic. And so also the map mu epsilon to u mu epsilon is analytic. And so also this vector depends analytically on the parameters. Okay. Okay. Moreover, and now let's come to the additional property of the basis. Moreover, you have is moreover. So what about the unperturbed basis? So the unperturbed basis, so if the operator were self-adjoint, U would be orthogonal, unitary. And so if the basis, if the original basis, the original vectors, if the unperturbed vectors are orthogonal, they would descend into orthogonal vectors. But now the operator is now we are in the symplectic world, in the Hamiltonian. So the important property is not orthogonality between the vectors, is that the vectors, the unperturbed vectors, are symplectic. Meaning, in this case, that if I make J f k plus f k minus, you can check it, this is -1, and instead all the others are 0, J f k plus are 0, and also if I make J f1 sigma f0 sigma prime, this is always 0. And moreover, these vectors are also reversible, meaning that if you make rho bar f1 plus, so rho bar, remember that what was rho bar doing? Rho bar was changing, rho bar is the map, rho bar eta x psi x, second component, so f1, f2, f1 x, f2 x, this is f1 minus x conjugate and minus f2 minus x conjugate. So if you apply rho bar to f1 plus, you get again f1 plus. If you apply rho bar to f1 minus, you get minus f1 minus. And if you apply rho bar to f0 plus, you get f0 plus. And if you apply rho bar to f0 minus, you get minus f0 minus. Okay. Okay, then these properties are inherited also by the perturbed basis. Okay, so these vectors will fix exactly the same properties, thanks to the properties of the of U and the original property. So example, let me check. Okay, so these are true. These are property. This property holds properties hold also for the perturbed basis. indeed, for example, let me check one. So let me check one of the two for you. So let's check, for example, J F1 plus mu epsilon against F1 minus mu epsilon. But what is this? So by definition, this is J F1 plus mu epsilon. What is this? Is by definition U mu epsilon F1 plus the aperture one, U mu epsilon F1 minus the aperture one. Then you take this, you take the adjoint, you bring it to the other side. This is U star J U, but U star J U, U is symplectic, U star J U is J, and so this is J F1 plus F1 minus, and so this is minus 1. Same for all the rest. So now the basis is symplectic. So let me check, and then let me check, for example, the reversibility, but this is also the same. Let me do this small corner, but if you do now rho bar, we do it here. If you do rho bar F1 plus mu epsilon, what is this? So this is rho bar U mu epsilon F1 plus, and what is this? So U is what is U? U is reversible preserving, reversibility preserving, which means that it commutes with rho bar. And so this is U mu epsilon rho bar F1 plus. They commute, and so I have rho bar U mu epsilon applied to F1 plus, but this is exactly the definition of F1 plus mu epsilon. Okay, so the basis, the perturbed basis, is depends analytically on mu epsilon. It is symplectic in the sense that it is process properties, and it is reversible in the sense that it is these other 4 properties. Now it's time to use these properties. It's time to use these properties. Yes.
So these properties and these perturbed vectors only exist for small unit epsilon.
Which properties? No, these property are cioè you can define these property are algebraic.
Oh, sorry, not
So you can
sorry, the construction of the perturb like that. F plus minus.
Yes, they exist. You can define the spectrum of vectors.
Only for small enough.
I mean, small enough. So what is the limit? The limit is when if you increase with epsilon, you might have at some point you see this 4 eigenvalue split, but also the other eigenvalue split. So this construction you can do it until you have some other collision. So till these 4 eigenvalues stay isolated from the others and there are no other collisions, then you get to this.
Because earlier on we showed that the P mu epsilon is close to P00 or P mu epsilon minus P00 as norm less than 1.
Yes, but yes, but what actually you're right, but what actually matters is that there are no other collisions.
Right. Oh, thank you.
I'm saying so you need construction to epsilon smaller, and then you can analytically continue also for larger values, and then another when there are other conditions happening, becomes excellence.
Now, because you need there are no other conditions, because you want constant the dimension of
Yes.
the invariant subspace.
Yes.
So there. Because
Exactly.
otherwise you would have a jump in the dimension,
Yes.
which would be the integer. It's a quite a different component. So, but one line of the jump
Yes.
Because at a certain moment you wrote dimension is equal dimension.
Exactly.
Uh,
Which is
This is trivially depending on the fact that they assume integer values, so
yes.
with respect to analytic.
Yes.
But
So for sure you can continue this the construction till you avoid the collision of this form with other eigenvalues. Right there. Okay. So now it's time to use all these properties.
otherwise you should be able to construct the composition of the space. I don't see any case where you can decompose the components of the solutions, or you can project on some spaces with different dimensions, you know. But
Yes, but it becomes tricky because so what happens because what happens is that you have these two. Then, for example, like if you increase mu, you keep increasing mu. So first they split, they make this. So two make this, but then you have two other eigenvalues. So you have four eigenvalues when you use
can you collide with the 12?
but then there are other eigenvalues up. And then when you keep increasing mu, so this goes up, this goes down, and so they collide here at some point. And when they collide, they split. And they make an isola. So it's very difficult to keep track of this we are not
In principle, you could have the projector taking care of the 8 and the solar.
no, yes. Yes. But there are
So the solution can be decomposed in this case in one component due to the isola, but possibly there are some interaction. So can you keep separated the completely?
for when you keep increasing we can do something we can do something in higher dimensional problem on which we are working on. Then we have one parameter more, and then we can do something like this. This problem not yet. So for the 2D.
No, just it's a curiosity to understand how far you can push things
No,
to the extreme.
we have tried, but for the moment we don't get a shot. Push this as you want. And then another thing that you use that now is important to see is that you lose control of the data size of the conditions. So for this instance, is also something which we control, but we not be able to control. So it's not necessarily has to try to do so. Okay, so okay, so lemma. So take f now, f1 plus, f1 minus, f0 plus, f0 minus, any symplectic and reversible basis of V mu epsilon, so not necessarily the one that we constructed, so any basis which fulfills these properties. Then the action L mu epsilon from V mu epsilon into V mu epsilon is represented by a 4 times 4 matrix of the following form: L mu epsilon equal J2, 0, 0, J2, and E, F, F star, G, where J2 is the 2 times 2 matrix 0, 1, minus 1, 0. E is self-adjoint. G is self-adjoint. And tell the structure, and moreover, E is given by what? So E is a 2 by 2 matrix given by the scalar product between B mu epsilon F1 plus F1 plus. Here we have B mu epsilon F1 minus F1 plus. Here you have B mu epsilon F1 plus F1 plus, and here you have B mu epsilon F1 minus F1 minus. This is E, and then G is the same, but with 1 replaced by 0. And instead, F has sorry, maybe this is not very clear at this. So let me write it like this. Sorry, let me do like this. L mu epsilon is equal to this metric J2, 0, 0, J2, and the matrix B mu epsilon, so which mu epsilon is done by B mu epsilon equal E. Let me write with B mu epsilon. B mu epsilon is a 4 times 4 matrix done by this. So you have the scalar product of B mu epsilon, which is the operator there, acting on you have F1 plus, F1 plus, space, sorry. Let me try to make the B just B mu epsilon 4 times 4 matrix. So B mu epsilon F1 plus, F1 plus. Then I have, so here I take in the first column, I take all the product F1 plus, F1 minus, F1 plus, F0 plus, B mu epsilon F1 plus, F0 minus. This is the first column. Then the second column, you have B mu epsilon F1 minus, scalar product F1 plus, B mu epsilon F1 minus, scalar product F1 minus. Here you have B mu epsilon F1 minus F0 plus, and here you have B mu epsilon F1 minus F0 minus. And the third column, and then I stop writing, B mu epsilon F, this is 0 plus F1 plus. And then you understand how it goes on. F0 plus, F1 minus, and so on. And then you have the last column, which is that it starts with B mu epsilon F0 minus F1 plus, and you understand how it goes on. And then I call this E. I call this instead 4 times 4 block F, 2 times 2 block F. This is F star. And this last block, I call it G. And you see immediately that P is self-adjoint because the operator B is self-adjoint. And the same happens here. And moreover, so here you see that, so the matrix representing the action of the operator on this 4 times 4 matrix, it has an Hamiltonian, inherently the sort of Hamiltonian structure, in the sense that it is this operator, which is Q adjoint, times a new operator B, a new metric. Okay, so this B, is it clear that this B is not this B? Also, the notation is the same. So this B, the B inside here, the B inside this here is this operator B. Okay, it's the B of the J acting on the vectors, and instead this B, I don't know how to, let me try to write it like this. So try to write it dotted. Okay. And moreover, so over here, but the entries of this matrix, the entries of B, are alternatively real and pure imaginary. So this is real, this is pure imaginary, this is real, this is pure imaginary, and so on. Okay. Okay, so let me convince you, or let me sketch the proof. I mean, I will not do the proof, but I will sketch the proof. My proof is not is quite easy now, because what do you need to do? So you need to represent the vector. So if you have a vector f in epsilon, what you want to do, and you have a basis which is symplectic and reversible, so you want to represent f on this basis. So what does it mean? Write f as alpha 1 plus, a linear combination f alpha 1 minus, f1 minus, alpha 0 plus, f0 plus, alpha 0 minus, f0 minus, and you want the coefficients. And I exploited this. So if it was, say, the basis were orthogonal, take the scalar product, the basis is symplectic, so you need to take the symplectic scalar product, meaning that you apply J, JF, and then take the scalar product, for example, with F1 plus. When you do this, what do you get? So you get alpha 1 plus, J F1 plus, scalar product with F1 plus, this is symplectic, this is 0. They are 0, except this one, which gives you the coefficient. So this is alpha 1 minus JF, JF1 minus, F1 minus, F1 plus, and this is minus 1. No, this is 1. So this is alpha 1 minus. And this way you compute all the other coefficients. Then what you need to do to write the matrix which represent the action, so you need to understand how L mu epsilon F1 plus, you need to understand the coefficients of this object on the basis. So we need to understand the coefficient of this on the basis. Okay, but we just compute the coefficient. What is, for example, alpha 1 minus? What is this? Alpha 1 minus, we just computed. Alpha 1 minus is, I need to take, what is alpha 1 minus? Alpha 1 minus, I need to take J, the vector, so J, L, mu epsilon, F1 plus, scalar product with F1 plus. Okay, but L is symplectic. So no, L is a Victorian. So L is J, B, mu epsilon. J squared is minus identity, and so this is minus B, mu epsilon, F1 plus, F1 plus. You do this computation for all the vectors, and you realize that the matrix representing the action has exactly this structure here. And about the fact that, for example, this coefficient is real, so this follows from the reversibility property of the basis. Okay, if you exploit this, you will find that the first vector is real. The first element is real. Okay, now and so the next goal, okay. So you have this matrix, so this is the matrix representing the object. Now, what we need to do is to get the expansion of this object. And so what we prove, and project is point tomorrow, so let me state the result. So it's an expansion of the matrix element of this 4x4 matrix. And so the proposition is that actually E, the first block, expand the structure, so it has epsilon square, and then a perturbation, a terms of higher order, which has the 0 for the epsilon and for the mu epsilon square, minus mu square over 8, 1 plus r mu epsilon. Then I have I, 1 over 2 mu, plus a remainder for the mu epsilon square, mu square epsilon, mu cube. Here it's the same as this element, so these are the same, and then you have here minus mu square over 8, 1 plus another remainder epsilon mu. And then instead the matrix G is 1 plus a remainder epsilon mu. Then you have here already a remainder, so this element is pure imaginary, and it is a remainder mu epsilon. And this you have I are the same element, a remainder. And here you have the mu plus the remainder, mu epsilon. And then you have F, which is this one, which is a remainder of order epsilon cube of order mu epsilon square, mu square epsilon, mu to the cube. I have 4 mu epsilon, mu to the cube. I another remainder different to the epsilon cube. Another remainder, the final remainder mu cube epsilon. Okay, these are the point scheduled for tomorrow. And what I want to, okay, and but let me say immediately a consequence. So what do we have now? Let's just look at the block. Let's just look at the blockchain. So what is the spec? Okay, so now we have matrix. So what is L? So L mu epsilon, what is J2, 0, 0, J2 applied to this matrix. So it is J2E, J2F, J2F star, J2G. What is the spectrum? Let me look just at this block, and let me just understand the spectrum of this block. So J2, so I remember that E, the matrix that is it is self-adjoint matrix, and I have the element, so this is a matrix of the form let me compute directly. Let me compute directly this matrix. So this matrix is J2E is what? J2E is so the two elements, you see the two elements on the out diagonal are the same. So when I multiply by J, they go on the diagonal and they are the same. So and they are purely imaginary. 1 over mu plus the remainder. Then here I have minus mu squared over 8, 1 plus a remainder. And here I have minus epsilon squared, 1 plus a remainder. plus mu squared over 8, 1 plus the remainder, and here I have the same element that I have. I 1 over 2 mu plus the remainder. Okay, so these two are the same. And so I can bring them out. Okay, so these are diagonal, the diagonal piece. So I can bring it out plus I mu over 2 plus the remainder. And now look at this matrix, and now you understand immediately when this matrix has stable eigenvalues. Because for this matrix, to have a stable, so the eigenvalues of this matrix of J2E are lambda plus minus equal this part, which is constant, I mu over 2 plus the remainder, plus, and then what we have here is you compute, so this is very easy now. This is modulus of mu over beta square root of epsilon square 1 plus the remainder minus mu square over 8 1 plus the remainder. So you see these are the eigenvalues. So this becomes unstable. This matrix has two unstable eigenvalues if mu is smaller than epsilon squared. And so this matrix exhibit the Benjamin-Fehr stability. And instead, the two eigenvalues of this matrix are pure imaginary. They will stay pure imaginary. And now there is a problem. Okay, so the message is that this matrix you compute it now as the correct Benjamin-Fehr stability. These are pure imaginary, but there is a coupling. And so the next step will be to decouple, to conjugate this matrix, to make a change of coordinates in order to conjugate this matrix to a block diagonal matrix in which we remove the outer diagonal term. So we want to find the change of coordinate phi such that phi minus 1 L mu epsilon phi, it has the new form J2E 0, cioè a new matrix here in U 0 0 J2G new, and in such a way that this matrix J2E such that E is more or less of the same size. It has the element of the same size as E in such a way that you preserve the Benjamin-Fehr stability here, and also G mu it will be the same size of G, but not these two blocks are 0, and therefore the eigenvalues are perfectly the Benjamin-Fehr stability. And okay, so I think I can stop. Then tomorrow I will sketch the proof with a few words about this theorem, and then we will develop the coupling. Okay, thank you.